Here's the video to explain why you should even care about these sum or difference identities. Alright, and really, I guess it's why you care for the Regents exam, not why you care in your own personal life. Okay, but the thing is that these identities kind of give us a way to find exact trig values for more than what we've already been able to do. Okay, remember, we know how to find exact trig values using the unit circle or using those special right triangles. Okay, we can do a little recap for exact trig. Okay, if we look at the unit circle, and I used this in the last video that you guys watched, here's 90 degrees, which is the same thing as pi over 2 radians. Here would be 180 degrees, which is the same thing as pi radians. This is 270, which is 3 pi over 2 radians. And this would be 0 degrees, 360 degrees, which is 2 pi radians. So from this, using the fact that cosines are x's and sines are y's, we can find the cosine and sine of all these values, right? Like the cosine of 90, which we could write as the cosine of pi over 2. Well, that's just the x value up here at 90 degrees, and that's just 0. Okay, similarly, we could do the sine of pi over 2, or 90 degrees. That's the y value up there, which is just 1. Okay? We could also do, say, the sine of 3 pi over 2. Okay, we know that 3 pi over 2 is the same thing as 270 degrees, which is hanging out right down here. And the y value there is -1. We can do the cosine of 3 pi over 2, which is 270 degrees. And that's the x value hanging out down here, which is just 0. Okay, so we can do this at 180, 360. If we keep going around and around and around. So this, we can do it for 450 degrees, because that's just going around once and then coming back. So we know how to find exact trig values for pretty much anything that's a multiple of 90. Okay, and then we stepped it up a little bit and we used special right triangles. We had our 30, 60, 90 triangle. Okay, and remember, 30 degrees is the same thing as pi over 6 radians, and 60 degrees is the same thing as pi over 3 radians. Okay, and we could fill in there because we, had this whole video of how this was going to be 1x, everything that's across from the 30. What's across from the hypotenuse, the right angle, that's 2x. And then when we go across from the 60, that's going to be x radical 3. So then we could just use SOHCAHTOA and find exact trig values for 30 and 60, and then anything that had a reference angle of 30 and 60, because then it was using this special right triangle, and then we just had to mess with the signs. All right, for example, we could do, let's say the cosine of 120 degrees. Well, I don't know the cosine of 120 degrees. That's not in the special right triangle. That's not something really nice on the unit circle. But if I look on a graph, 120 degrees is over here in quadrant 2. And that has a reference angle of 60. So if I drop in this little perpendicular, there is my 30, 60, 90 triangle that I do have exact trig values for. And we know that the cosine of 60 is, remember, cosine is adjacent over hypotenuse, a over h. So the cosine of 60 is going to be 1x over 2x. So it's going to be the same thing over here for 120, 1 over 2. Except since I'm in quadrant 2, my cosines are negative. So we make it negative. Okay? So this gave us exact trig values for 30 and 60 and anything with a reference angle of 30 and 60. We also had our 45, 45, 90 triangle. A nice isosceles, right? And 45 is the same thing as pi over 4 radians. And these have the special side ratios of 1x, 1x, and x radical 2. So I'm not going to do an example, but the same thing that I did for 120, I can find exact trig values for 45 degrees or anything with a reference angle of 45 degrees, which was super cool. Okay, but not everything is going to have a reference angle of 30, 60, or 45. So these sum and difference formulas kind of give us another way to figure those out. Okay, for example, say if I asked you to find, let's say find the exact measure for, and let's say this is going to be the sine of 75 degrees. The sine of 75 degrees. Now looking at the sine of 75, all right, 75 is definitely in quadrant 1, so it is its own reference angle. All right, and 75 is not something that's nice on the unit circle, and it's not a part of our special right triangles. So what we're going to do is we're going to get really creative. Okay, and what I'm going to do is I'm going to take the sine of 75 and I want to rewrite it using things that I do know how to find the sine of and using the sum or difference formula. All right, for instance, isn't it true that I can rewrite 75 as 45 plus 30? Right, 75 is just 45 plus 30. And now this is super awesome because I just took 75, which is something that I have no idea what an exact trig value would be for, but I do know exact trig values for 45 and 30 because those are from my special right triangles. So now I can use these special right values along with this formula that we just learned, and I can actually find an exact value for the sine of 75. All right, let me rewrite this. Make it looks messy to me. So we took the sine of 75, which I have no idea what an exact value would be. And we said, well, let's let that be the sine of 30 plus 45. Because 75 is equal to 35 plus 45. Then, using that sum formula that we learned, we can say, well, this is really equal to sine, cosine, cosine, sine. Okay? So it's the same sine formula, except now instead of doing A plus B, I'm doing 30 plus 45. So I've got sine, cosine, cosine, sine. And now we have values for all of these using those special right triangles. Okay, first let's tackle the 30. Here's 30, here's 60. I've got 1x, 2x, x radical 3. I told you guys I have to draw this every time I do this. So for this sine of 30, I'm right here, and I'll even write SOHCAHTOA so I don't screw this up. Sine is opposite over hypotenuse, so I'm doing the opposite side over the hypotenuse. That's going to be 1/2. And then I'll wait to do the 45, but I can do the cosine of 30. All right, I'll do that in a different color. The cosine of 30 is adjacent over hypotenuse, so that's going to be the square root of 3 over 2. And now I'm done with this triangle, so let me erase it. And now I can move on to my 45-45 triangle because that's what I've left in here. Now, both of these angles are 45, so it doesn't really matter which one you pick. I'll pick this one right here. When I do the cosine of 45, that's adjacent over hypotenuse. So that's going to be 1 over the square root of 2, but I'm going to rationalize that. So I get the square root of 2 over 2. So that's what I'm going to throw in here. And the same thing is going to happen when I do the sine of 45, right? Because my opposite side is also 1/2 over the square root of 2. So I'm going to get the same thing here. And now we can just simplify this like we've been doing with these formulas. So here I get the square root of 2 over 4 plus, that's going to be the square root of 6 over 4. And that's about it. Square root of 2 plus the square root of 6 all over 4. Done. Boom, baby. Okay? We got an exact value. No rounding, no anything messy. For the sine of 75 by using trig values that we knew and this new formula that we got. Okay, I'm going to do, actually I'm going to do this example again, but I'm going to do it a little different. Okay, so I'll extend my page. I'm still going to find the exact trig value of the sine of 75. But instead of writing 75 as 30 plus 45, instead I'm going to write 75 as 120 minus 45. Alright, so if this is how you saw 75, cool beans, man. Go for you. Because we can still use the exact trig values because 120 has a reference angle of 60. And now we can just use the distance formula and we'll be good to go. Alright, so this is really going to be sine, cosine, cosine, sine. Sine, cosine, cosine, sine. Remember, the minus stays a minus. And let's do the 120 first. Okay, 120 has a reference angle of 60, so I'm back in my 30, 60, 90 triangle. And I'm using SOHCAHTOA, so I'll write that. Now, reference angle 60, so here I am. So for sine, it's opposite over hypotenuse. So it's going to be the square root of 3 over 2. And it's going to stay positive because sine is still positive for 120. When I do the cosine of 120, I'm still using 60 as my reference angle. Cosine is going to be adjacent over hypotenuse. So that's going to be 1/2. But 120 is in quadrant 2 where cosines are negative. So that's going to be negative 1/2. I've still got this minus sign in between. And then I'll come over on this side and I'll do my 45, 45. When I do the cosine of 45, that's going to be adjacent over hypotenuse. So it's going to be that same rationalizing stuff I did up top. And I'm going to get the square root of 2 over 2. Same thing over here. And then when you simplify this, this is going to be the square root of 6 over 4 minus negative the square root of 2 over 2. And minus the minus is really plus. So this is the square root of 6 plus the square root of 2 over, I'm sorry, there should be a 4. And there we go, I got the same thing. Okay, so 2 ways to do this. Either way, it's using exact trig values and the sum or the difference formula to get exact values for what we want. All right, let's look at how I'm doing on time. Pretty good. So I think I'm going to do I want to do another example? Do I not want to do another example? This is what I'm going to do, because this is cool, and we're going to do some more practice with this later. But remember, we can also use these sum or difference formulas to prove trig identities, all right? I know how much we hate doing it, but It's part of the Regents exam. Okay, so let's do, what do I want to prove? Let's prove that the sine of 270 plus x is going to be equal to negative the cosine of x. All right, let's prove this using this new sine sum identity that we know. I'll make that plus sign next there. Okay? Clearly the left side is the more complicated, so I will break that down. That is going to be sine, cosine, cosine, sine. Okay? So remember, it goes sine, cosine, cosine, sine, left to right. The operation stays the same. And we should be happy because 270 is on the unit circle. That is something we have an exact value for. 270 is down here. The x-coordinate there is 0, so the cosine of 270 is just going to be 0. And the y-coordinate down there is negative 1, so this is just going to be negative 1. Times the cosine of x. I'll fill in all this other stuff. And negative 1 times cosine x is just negative cosine x. And 0 times anything is just 0, so that goes away. And boom. Proof done. Okay, so yet another identity to use in our trig proofs. That's it. I am